Feels like it's been years since I studied. So, about that midterm. You might be wondering how I did. Well, the short answer is it's complicated. The long answer is everyone, including me, got their asses handed to them, so there will probably be a curve, but I do not know what that curve will look like, nor do I know what my score is right now. It was one of the strangest calculus tests that I have ever taken, so I don't really know where to start with studying tonight. I think I might as well just go on the regular schedule again of covering material that I learned in class that day. So, without further ado, let's get started on that, shall we? So first on the chopping block tonight is reparameterization, a subject that was on the midterm, but we first covered it in lecture today. I'm not going to talk about whether I think that it was a good idea to have it on the midterm or not. I'm just going to deal with the information as it comes to me. With that out of the way, reparameterization is when we take a position vector or equation and we put it into, well, new parameters. These parameters can depend upon the situation or the strategy that you are using. Our job is going to be finding phi of tau. Again, phi of tau is going to be different depending on what strategy we want to use. Let's recall the vector parametric equation t, t squared, t cubed. Let us also recall that r prime is going to be the velocity of the position equation r. We want to reparameterize r in terms of unit speed. Now, this can be very useful because we recall that a parametric equation is in terms of t and a vector. T is a scalar, and you can get any point on the line just by multiplying the vector by a certain scalar. Instead of having any random scalar t, we are going to reparameterize this equation in terms of unit speed. So instead of t, we are going to have a speed vector with length 1. A unit speed vector, dare I say. We found velocity. The speed vector is going to be the magnitude of that velocity. Oh, I've played myself by choosing this equation. Because the next step is to find the inverse of this. And algebraically, it's pretty tricky for this. Because we can square both sides, and we can move the 1 over to the other side. We can even take out a factor of 4t squared. But here we see that there are going to be multiple solutions to this equation. So there are multiple inverses to this particular function. And that's no good. But in general, if you haven't played yourself like I have, the strategy for reparameterizing in terms of unit speed is going to be A, you need to find the speed function. B, you need to find the inverse of the speed function. And then C, the final step, you need to plug the inverse of the speed function back in to the original position vector. But this isn't the only strategy that we have. I got this one from the textbook instead of making it up on the fly, so it should hopefully work. In order to reparameterize this equation with respect to arc length, we start the same way that we started our previous strategy. First, we take the derivative of the position function. New room, no time to complain. So we have our derivative. Now we want to find the arc length. And we are going to write our arc length in terms of s of t. And that's going to be important later. But for now, we just solve the arc length normally. Our bounds are from 0 to t, signifying that we are parameterizing in the direction of increasing t. And the inside of our integral is just the square root of the sum of all of the components squared. Don't forget dt. This is actually du, not dt. Because we're not integrating along t. T is something that we're going to add in later. Now we have s of t. So now we need to find the inverse of this, which is, of course, s divided by root 29. So our new r of t is going to have this plugged in for every single t. This is going to be our final reparameterization. General strategy for reparameterizing along arc length: check which direction you are reparameterizing in, find the derivative, find the arc length in terms of du, find the inverse of your new arc length equation, and then, finally, replug the inverse back into the original position vector. When we last left off in statics, we had just been introduced to the moment generated by a force acting about an axis. The magnitude of a moment acting about an axis going through the points O and L is equal to the triple product of lambda OL, which is a unit vector pointing in the direction of the axis, dotted with R, which is the position vector of any point on the axis with the point of application of the force out in space crossed with the actual force. It's a lot simpler to do, I swear. Anyway, triple product is just 3x3 matrix. We know how to do determinants, easy peasy. In honor of Valentine's Day being this Friday, we were introduced to couples. How romantic. I should put some like Tchaikovsky music here. Now, couples are two coplanar forces that are equal in magnitude but opposite in direction. Couples generate a moment of force along an axis that is running perpendicular to the plane that they are in and running through the point that the couples are rotating around. The moment of force generated by a couple can be defined as R cross F, where R is the position vector between the 2 points of application, and R is the magnitude of one of the couples. As with any cross product, we can define this as magnitude of R times magnitude of F times sine of theta, theta being the angle in between the line of action and R. If we are given the perpendicular distance between two couples, then we can simply write the moment of force generated as d times f, because we know, of course, that sine of 90 is just 1. Simple enough to start. We can define a moment of force generated by a couple by drawing the axis it is acting about. Although it is important to realize that these couples are still only going to be causing clockwise or counterclockwise rotation on this plane. We can also add a system of couples together. If we imagine that negative f1 and f1 are on the same plane, and negative f2 and f2 are on the same plane, then we will get a resultant couple after we add them together. The moment generated by the resultant couple will be r, the distance in between the points of application, crossed with the magnitude of one of the couples, which is going to equal r cross f1 plus f2. Again, pretty simple. A quick correction, I said the magnitude of one of the couples, it's not. You are crossing r, the position vector between the 2 points of application of the couples, with a force vector of one of the couples. Two more things I want to do with couples tonight. If you have a moment about an axis, you can find the components of that moment along the x, y, and z axis by decomposing it using direction cosines. And this is going to be important when we decide that we want to start adding a little bit more complicated moments. So now let's imagine that we have a force acting upon this object somewhere on it. We know that the position vector between the origin and the point of application of the force has magnitude r. So we want to use couples to be able to center the effects of this force directly on the origin. We draw two equal and opposite forces on the origin. Since they're equal and opposite, the net effect on the object is going to be equal to 0. But we notice that these two forces form a bit of a couple, don't they? So finally, we can draw this force as a couple and a force acting on the origin. This, in statics, we call a force-couple system, and it is going to be extremely useful for resolving rigid body static problems, which we just got introduced to today. But anyway, the moment of force about the origin is going to be given by r crossed with f, which looks pretty familiar. The force vector left over is just going to stay there and be the same, acting in the same direction, but just at a different point, which is not something the principle of transmissibility allowed us to do. Remember, we could only transfer vectors along their line of action in order to not alter the effect on an object. But with this, we can move these things wherever we want, even to points that aren't the origin. So let's say that we have a force vector acting at point A, which is r away from the origin, and we want to move it so that it is a moment couple system acting at point A prime. Our force is acting parallel to the original force, and we have a new moment generated by the couples that we use to get the force from here to here. The moment about A prime is going to be given by S prime crossed with F. But because of vector algebra, we know that A plus S is going to give us S prime, so we can write this as A plus S crossed with F. So the moment at any point given by a force at another point is the cross product of the position vector from the first point to the origin plus the origin to the second point crossed with F. Goodness gracious me. Well, without mistakes, we wouldn't learn. Positivity. There's still more statics to do, but I want to be able to get in at least the bare minimum of studying for physics tonight. There is a bit of a content deficit that I need to make up. So let's get started, shall we? Note to self, don't leave physics until last. I'm sorry to say, but I don't have the energy for that right now. Learning electric potential, and it is a bit more difficult for me to grasp than continuous charge distribution, or Coulomb's law, or Gauss's law, which kind of shocks me because Gauss's law was a little bit difficult for me to understand at first. But I have faith that I will get it. I'm going to do it first, tomorrow, before public policy, which is a little bit of a risk since we have a midterm on Thursday. But I think that'll about do it for tonight. Thank you so much for watching. I'll see y'all tomorrow.